What is unified atomic mass unit? The simple answer is it is a unit of mass, just like kilogram is a unit of mass. And we are all very familiar with this unit kilogram because we use it in our daily lives to measure and express the masses of common objects that we see. In a fruit shop, you may find the mass of a bag of oranges is 4.6 kilograms. You may find the mass of a book is 1.8 kilograms and so on. But what do we mean when we say the mass of this bag is 4.6 kilograms? What we mean is its mass is 4.6 times whatever mass we are calling 1 kilogram. So what we are doing in this measurement is we are comparing the mass of this bag with whatever mass we are calling 1 kilogram. That is what we do by using a scale or a balance, right? So, measurement is always a comparison. Then what is 1 kilogram? Until the year 2019, 1 kilogram was defined as the mass of a small cylinder made of an alloy of two metals, namely platinum and iridium. Whatever mass is present in this particular cylinder, by definition, it is taken as 1 kilogram. So, when we say the mass of this bag is 4.6 kilograms, what we mean is it has 4.6 times as much mass as there is in this particular platinum iridium cylinder that is safely locked away somewhere in Paris. And the kilogram stones you see in your local grocery store are inexpensive copies of this particular cylinder. Now the question is, why did we take this mass as the size of 1 kilogram? Why not something much bigger or much smaller than this cylinder as the size of 1 kilogram? The reason is, when we compare the masses of common objects with this particular mass that we are calling 1 kilogram, we get numbers like these. Numbers like these are convenient to us. Simple whole numbers and decimals like these are convenient to us because we can easily compare them with one another and we can easily remember them. Now let us say we have a bag of apples and a bag of oranges with us, and we wanted to know which of these two bags is heavier. For this, all you have to do is go to a nearby fruit shop and weigh them. Let us say the bag of apples weighs 4.4 kilograms and the bag of oranges weighs 4.6 kilograms. Now looking at these two measurements, we can easily understand that the bag of oranges is slightly heavier. And for this comparison, it is sufficient if you measure their masses up to 1 decimal place. But on the other hand, say we have a single rice grain and a single mustard seed, and we wanted to know which of these two is heavier. Now for that you have to weigh them, but where do you go to weigh a single rice grain and a single mustard seed? You cannot go to a grocery store to weigh them. So for this, first you have to find a good laboratory. See, it is already becoming difficult. Now let us say we finally found a scale that can weigh them. And say we found the mass of the rice grain to be 0.000002 kilograms and that of the mustard seed also to be 0.000002 kilograms. Now, by looking at these two measurements, we may conclude that these two have the same mass, but are we sure? Maybe not, because here we measured their masses only up to one significant digit and they are found to be the same. But to be sure, we need to know the values of more digits in their measurements. Say the second time we measured their masses up to 3 significant digits. Say we found the mass of this grain to be, after so many digits, 2, 7, 9 kilograms, and that of the mustard seed to be, after so many zeros, 2, 1, 3 kilograms. Now by looking at these two, we can easily understand that the rice grain is heavier than the mustard seed. So what I am trying to say here is, if you use a unit as big as a kilogram to compare the masses of such small things like a rice grain and a mustard seed, you have to measure their masses to more significant digits. And measuring anything to more significant digits is more difficult. Secondly, do you like numbers like these? These are awkward numbers. We don't want to deal with such numbers. They are not convenient to us. So for these reasons, kilogram is not a convenient unit to measure and compare the masses of a rice grain and a mustard seed that we could see. Then imagine comparing the masses of atoms that are astronomically smaller than a rice grain and a mustard seed. Do you think kilogram is a convenient and appropriate unit for measuring and comparing the masses of atoms? Think about it. So what I am trying to say is, kilogram is too big a unit to measure and compare the masses of extremely tiny particles like atoms. Kilogram is neither appropriate nor convenient to measure the masses of atoms for two reasons. To compare the masses of atoms in kilograms, you have to measure their masses to a high degree of precision, which is difficult. Secondly, even if you somehow manage to measure them to some degree of precision, the numbers you get are really awkward. See, this is the mass of a single sodium atom in kilograms. Do you like to memorize this number? Do you want to deal with this number? I don't think so. Now, John Dalton was the first scientist to measure and compare the masses of atoms. But from the times of John Dalton to the present day, we never liked the unit kilogram to measure and compare the masses of atoms. We always used other standards that are much smaller than a kilogram to measure the masses of atoms. John Dalton originally used the mass of one hydrogen atom as the standard. Later on, for some time, we used 1/16th of the mass of one oxygen atom as the standard. Then finally, for some good reasons, in 1961, we came up with the latest standard or unit that is called Unified Atomic Mass Unit. It is simply a unit to measure the masses of atoms, atomic mass unit. And by definition, one unified atomic mass unit is equal to 1/12 of the mass of an atom of C12 isotope. Just like 1 kilogram by definition was equal to the mass of this particular cylinder. And the symbol for unified atomic mass is small u. And in honor of John Dalton, it is also called Dalton. Unified atomic mass unit and Dalton are one and the same. And the symbol for Dalton is dA. So 1 unified atomic mass unit is equal to 1 U, that is equal to 1 dA. Today, using advanced mass spectrometers, we can measure the masses of atoms, ions, subatomic particles, molecules to a very high degree of precision in unified atomic mass units, that is in U. And we found the mass of one sodium atom to be approximately 23 U. This is the mass of a sodium atom in U and this in kilograms. Which one do you prefer? Obviously this one, right? Similarly, we found the mass of one nitrogen atom to be 14 U. What do we mean by that? We mean one nitrogen atom is 14 times as heavier as 1 U, and you know the size of 1 U, it is this. So a nitrogen atom is approximately 14 times as heavier as 1/12 of the mass of a C12 isotope, an atom of C12 isotope. That's what we mean by 14U. The mass of one helium atom is approximately 4U, and the mass of a chlorine atom is approximately 35.5U, and so on. So if you look at these numbers, these are either whole numbers or decimals that are also simple. So if you measure masses of atoms in U, you get convenient simple whole numbers or numbers that are close to whole numbers. Remember, mass of one atom, mass of an atom is also known as atomic mass. See, here it has 4 words, this has only 2 words. So atomic mass is a shorter name for mass of an atom. They are one and the same. Atomic mass is mass of an atom, and that represents mass of a single atom. So if someone asks for the atomic mass of sodium, it is 23U, not 23. You have to express it in the right units. See, if someone asks for your weight, you may say 55 kilograms or 60 kilograms. You would not simply say 55 or 60. Similarly, atomic mass is mass of a single atom. It represents the physical quantity called mass, so it must be expressed in the units of mass. And atomic masses are almost always expressed in unified atomic mass units. So what is the atomic mass of nitrogen? It is approximately 14U, not 14. The atomic mass of chlorine is 35.5U approximately, not 35.5. So don't ignore the unit.